right into this fascinating explainer. We're going to be looking at the unbreakable rules governing those magnets stuck to your fridge and unpacking a secret that has literally puzzled physicists for centuries. We're talking about the fundamental properties of magnetism, a force that permeates everything from massive, distant galaxies right down to the tiny, invisible atoms that make up our world. But despite it being everywhere, magnetism hides a deep mathematical and physical mystery that we are going to explore today. So we've all played with magnets at some point, right? Sticking them to things, feeling that invisible push and pull. But have you ever wondered what actually happens if you try to separate the North Pole from the South Pole by breaking it? Like, if you have a bar magnet and you take a hammer and just smash it right down the middle, do you finally get a North Pole in your left hand and a South Pole in your right hand? Well, you might think you'd finally isolate a single pole, but nope. You actually just get two smaller, slightly weaker magnets. Each new piece instantly has its own north and south pole, and no matter how many times you break it down all the way to the atomic level, you never ever get just one pole. Unlike electricity, where you can easily isolate a positive or negative charge, a true magnetic monopole, an isolated north or south charge, is, well, as far as our current understanding of the universe goes, a complete physical impossibility. All right, moving on to Section 1, the ancient magnetic mystery. Ever since the ancient Greeks discovered these cute little magnetic rocks on the island of Magnesia around 600 BC, which, fun fact, is actually where the word magnet comes from, scientists and philosophers have been totally captivated by this force. I mean, the Earth itself behaves like a giant magnet, which is exactly why our compass needles point north. But here's the crazy part. For over 2.5 millennia, humanity has been desperately searching for a single, isolated pole, and nature stubbornly refuses to give us one. Let's look at Section 2, Visualizing the Invisible Field. So, how do we investigate a mysterious force that we can't even see with our own eyes? Well, what's really interesting here is how sprinkling simple iron filings on a piece of glass makes those invisible magnetic field lines perfectly visible to us. The iron filings act like thousands of tiny compass needles jumping to attention, aligning themselves to create this beautiful, intuitive map of the magnetic field. You can literally see the shape of the force spreading out from the poles. Now, the crucial point is that these field lines follow 4 very strict rules, basically proving that what goes out must eventually loop back around. First off, unlike electric fields that can start at a positive charge and shoot off into infinity, magnetic field lines form continuous closed loops. Second, if you draw a tangent at any point on these curves, it gives you the exact direction of the net magnetic field right at that spot. Third, where the lines are packed tightly together, like right near the poles, that's where the magnetic field is strongest. And fourth, these lines never, ever intersect. If they did, it would mean the magnetic field had 2 different directions at the exact same point, which is mathematically impossible. No way. Up next, Section 3, the solenoid twin. So really understand why monopoles don't exist, we need to meet the bar magnet's secret's electric twin. This brilliantly illustrates how a simple, current-carrying solenoid, which is basically just a coil of wire with juice running through it, produces a magnetic field virtually identical to a solid bar magnet. If you map the far axial magnetic field of both, the math matches up perfectly. And that brings us to Ampere's brilliant hypothesis. He figured out that all magnetic phenomena can actually be explained in terms of circulating currents. So a bar magnet acts like it's packed with a vast number of tiny atomic-level circulating currents. Think about it. Just like cutting a solenoid in half simply gives you 2 smaller solenoids, cutting a bar magnet just gives you 2 smaller magnets. The field lines remain completely continuous, emerging from one face and entering the other. There's no isolated source, it's just loops all the way down. Which leads us to Section 4, the electrostatic mirror. Now let's explore how magnetism has a strangely familiar sibling in the physics world. Before we even look at the heavy math, we just have to realize that magnetism is kind of like looking at electrostatics in a mirror. You can actually translate complex electric equations into magnetic ones just by swapping out a few variables. If you take electricity's constant, the electric permittivity constant, and swap it out for magnetism's constant, the magnetic permeability constant, and then replace the electric dipole moment with the magnetic dipole moment, boom! You effortlessly translate the formulas and instantly have your magnetic field equations. Okay, let's dive into this awesome little cheat sheet to see how perfectly the equations for electric dipoles mirror the magnetic ones. Look at how beautifully symmetrical this physics is. The torque on a dipole in an external field is just the dipole moment crossed with the field. Whether it's electric or magnetic, the math doesn't care. And the potential energy, it's simply the negative dot product of the dipole moment and the field. It's the exact same behavior, just perfectly mapped onto a different fundamental force. And finally, Section 5, Gauss's law of magnetism. This brings us to the ultimate verdict and the grand climax of our magnetic mystery. The crucial point is beautifully summarized by Gauss's law of magnetism. See, in electrostatics, if you draw a closed imaginary surface around a positive charge, you have a net outward flux. Lines of force are literally leaving the surface. But in magnetism, because there are no isolated magnetic sources or sinks, the net flux through any closed surface is absolutely zero. And this brilliantly illustrates what that means in reality. Because of this law, for every single cute field line playfully leaving a closed area around a magnet, another one absolutely must come right back in. It is a perfect, inescapable balance. The simplest magnetic element isn't a point charge. It's a dipole, a current loop. The whole shebang in magnetism relies on this fundamental geometry of closed loops. So, I'm going to leave you with this mind-bending thought. What if we're wrong? If someone finally found a solitary magnetic pole tomorrow, how would it shatter everything we know about Gauss's law? If monopoles existed, the net magnetic flux through a closed surface wouldn't be zero anymore. It would actually be equal to the enclosed magnetic charge, completely mirroring electrostatics. It would trigger an absolute revolution in modern physics. But hey, until that day comes, the mystery of the missing monopole remains one of the most beautiful, unbroken rules of our universe. Thanks for joining me for this explainer, and keep questioning the invisible forces all around you.